All right. I'm going to go ahead a little early because I got a meeting that's going to take place. So let's assume we have a beam sitting here, and I'm going to say this is 10 long, and I'm going to list this as X. I'm going to do a variety of things. I'm going to put 100 pounds here at 2. I'm going to put 500 pounds here at 8. Here, I tell you what, since I'm going to do several things here. So I'm going to say this is 2, this is 8. Then I'm going to put a distributed load here of 50 pounds per foot. And then I'm just going to mix it up and put a triangular load on top of that. That says that pretty much starts, say, here at 5 and continues a distance of 2. And the height on the far end is going to be, let's see, 200 pounds per foot. So this is a lot going on. I'm going to show you how to use MATLAB to get the shear diagram and the moment diagram out of here. But before I do, I've got to identify that actually I have 4 loads. Now what I'm going to do is I do have reaction loads here. I'll call this the L, and I'll call this the R. But I'm going to go back and deal with those in a little bit. Normally you would deal with these first, but since I'm using MATLAB, I'm going to deal with those in a minute. So the first one, I've got F1 of X being 100 times a delta function, X minus 2. Now, maybe I'll color code these. So that one is that one. Now let me kind of, here, I may do multiples of these at the same time. Hang on here. I'm actually working in another window, and I'm going to switch to it in a second. Okay. So actually, that needs to have a minus sign in it because this is going to be the plus direction. So let me put a minus sign here. Okay, I'm sorry I'm quiet over here, but I am just, give me a second. I'll switch to this other screen in a minute. It is on another, completely other system. Okay. Okay, hang on. Sorry for the quietness. Okay. I'll get to it in a second. You can always spin past this. Well, you know what I might do first? I might do one of these and then move to the next one. So what I might do, here's what I think I'm going to do first. So I don't want to make this too overwhelming to begin with. We're just going to start here. And then we'll add these other loads as well. So what we'll do is do a load and check things out. So here's my 50. If you go in and look at this, okay, so if it's 50 pounds per running foot, then the total load is 10 times 50, or 500, which means for this one, 250 is carried here, 250 is carried there. So if you look at this, it's 250. Now this is extra material, so to speak, so we'll do the shear in a second, but here, the shear, okay, given that this is x, so sum the forces in the y equaling to 0. I don't know, we'll make this positive. Minus v plus 250 minus, this is my 50 per running foot, 50x. So that means v is going to be 250 minus 50x. And that's going to maintain itself throughout the entire diagram. So here you go. It's going to go, this point's going to be 250. So if you had the beam, and this is a very small portion, so this is like 0 essentially, 250, 250. The width here is 0. It tells you that it goes from 250 right there. Now, if you plug in v at x equal to 10, you get 250 minus 500, or minus 250. So you end up at minus 250. Now, let's look at the moment here. Well, I don't need to draw the arrow here. Here's your moment. So sum the moments equaling to 0. Go ahead and make this plus, would be m minus 250 times x. Now, what I've got to do in this proportion is the beam sits here. Equivalent load to that sits there. It's actually 50 times x. Its distance is x over 2. So what you get, and it is going in this direction. Sorry. 50 times x and x over 2 gives you your moment looking like, if I move that over, 250x minus 50x squared over 2. So first thing about this, here, wait a minute, was there another? No, this was the equation. First thing about this is if x equals 0, moment equals 0. If x equal to 10, then let's see, 250, I'm looking for the moment. Moment at x equal 10 would equal 250 times 10 minus 50 times 10 squared over 2 equals to 2500 minus 25 times 100, and gives you the moment of 0. So what you've got is a moment that sits here with no value here and no value here. Why? Because this is a simply supported beam. There is no applied moment at the ends. There is an applied shear, but there's no applied moment. Now, what happens to it? Well, let's see. Okay, I'm going to take a momentary, I'm over on the other machine. Sorry about that. Lost my pen. Here we go. So what you end up with is something that looks like so. Now I said this before, and I'm going to say it again, but what I'm going to do this time is I'm going to take this thing and move it over. And now I'm going to basically come in here and say my f of x is equal to 50. That is this function. Then I have a v is equal to, 250 minus 50x. And then I have a moment equal to 250x minus 25x squared. Looking at all these, I find a conclusion that I basically was talking about before, and that is, if I take this, I get that. And then if I take this, I get that. So if I differentiate running up this way, I can differentiate to get those values. But if I'm running this way, I integrate. So in other words, if I'm given this value and I want to find, okay, so I have a relationship, dv dx equals to f, where this is a function of x. I can say this, now here's what happens with this. Let's look at the right side. And this is, we're going to basically list this as not a definite interval, but indefinite interval. So if you have this being a constant, you can take it out and you'll have it. In this particular case, you'll have 50 You pull it out. Oops. 50x. Now, oh, and I have to basically realize that that was a arrow pointing down, so it's minus. The problem is I have a constant of integration here. So if I have a constant of integration here, what do I do to determine that constant? Well, in this particular case, you have a boundary condition, and that's that. Now that's actually the load, and it's 250. So if you put in x equals 0, you've got to get back this, because, which is what you have here, because it has to be such that this is, think of this in this particular way. This is a boundary. This is a boundary, the ends of the beam. In this particular case, you have an equation which has to meet that boundary. Turns out it meets the other boundary on the other side as well. So let's basically take this equation and integrate it. But before we do, let's do this, which leads us to this conclusion. Now I can stick this in here. Now I don't have that. So basically this is not a definite integral at this point. So I'm integrating 250 minus 50x dx. 250x is 50x squared over 2 plus some constant of integration. How do you determine this constant of integration? Well, now what happens here is quite interesting. On the end of the beam, there is no applied moment. There is an applied shear, not an applied moment. So therefore, technically, there is a constant of integration. It must be looked at. But in this case, my end condition is such that it's 0. So if you put in x here of 0, put in x here of 0, you'll have the conclusion that C2 is equal to 0. So in fact, you'll get that. And so that's essentially the case. Now, I went off and I did something in addition to that, in which I put a point load. And so what I'm going to do now is I'm going to use this space to the right. I'm going to consider this beam again. This time, it's going to be 10 long. It's going to have a load of 200 pounds exactly in the center of it. 5 and 5. Now you know the left end is going to be from some of the moments. Okay, feet, pounds. That this is going to be 100 over here, and it's going to be 100 over here. So now, how do you list this function? How do you list f of x in this case? Well, it's 200 times what's called the delta function, our Dirac delta, x minus 5. Now, what I'm going to do, okay, I'm going to kind of bounce back and forth here between a couple things. First thing I'm going to do is I'm going to say, okay, I know, okay, basically the equation that's set right here, and or basically the one under it, I'm basically now going to take an integration of 200 times delta x minus 5 dx, and that's going to be the shear. So how do you integrate this silly thing? Well, oh, and I have to realize, again, this is a minus and a minus. So that's a minus number because it's pointing down. So is this. So how do you identify this? Well, okay, now I'm here. I have MATLAB running in the other window. I don't have MATLAB on this machine, so I'm going to bounce back and forth here in a second. And I'm sorry there's little dead sections here. Okay. Okay. Let me see now if I can unfold this and refold it off of the stream the other way. So what I'll do is I'll stop the stream. I'm going to bring up the stream on the cell phone so you'll hear some echoing. Okay. Ah, I'm back. I'm using a different microphone and everything here. I'm using a different microphone and everything here. Let me turn the volume down. Okay, so what you see here in this particular area is the function. So if I do that, it just simply copies. So first thing I did is I made x symbolic. And then I basically created that function. Now I'm going to integrate that function, and I should actually say v equal to the integration of f with respect to x. Now, thing is, I can plot this, and it's all okay. I'm going to plot it from 0 to 10. But what you see is kind of interesting. Okay, well, let's see. How can I make this a little bigger? I think. So what you see is it's 100. And it goes over here to this point and drops down to minus 100. Now, as it turns out, there is a constant of integration. And this is basically a sine function, which changes sign. So let me bring this up and head back to the... I'm going to head back to the other portion, or the other screen. I'll release this one. Okay. So now I'm back on the Windows machine. So this thing, according to what I see, I'm going to look over my shoulder at the thing on the right. According to MATLAB, what this looks like is minus 100 times what's basically in MATLAB listed as this, sine of x minus 5. But there has to be a constant of integration. Okay. Now, we saw on the plot that it looked like this. where this was 100 and this was minus 100. As it turns out, if you zoom in on a section right there and look at it, where you're to the left of that 200-pound load, you see 100 and you see 100 here. So in fact, that's what it's supposed to be. So the constant of integration based upon this is 0. So there, in fact, is my shear diagram. So what does the moment diagram look like? Well, here we go. Okay, if this is the shear, let's see, for some reason I can't move to the right. Now, well, here. Okay, now I can. And so make these X's over here. So now, if I integrate the shear dx, get the moment. So now I'm going to integrate minus 100 SIGN x minus 5 dx equal to the moment. What does this do in MATLAB? Okay, so let me push us back to the other screen, to the other computer. Okay, we're at the other machine now. And we want to integrate moment is equal to the integral of the shear, and it's got to be with respect to x. So it looks like that. Now, you look at that and you're like, interesting. That's how MATLAB represents it, right? So let's do an F plot of the moment from 0 to 10. Oops. I'm going to do this way. And lo and behold, this is what you get. Now, I'm going to come back over here to the screen and take a look at this. Now, look at this real close. Okay, this is a part where we're going to bounce back and forth here a couple times. The screen, as I see it, shows a negative 500 at 0 and a negative 500 at 10. There is no applied moment there, so this means the moment, which is this right now, the moment is equal to the moment plus 500. The constant integration here is 500. Now if I go back a couple of steps and do the plot, here's what I see. I see it being a moment of 0 on the left and a moment of 0 on the right. And right in the middle, I see a moment of 500. Let me switch back and we'll... Okay, I'm back over here. So as it turns out, in a MATLAB sort of sense, this integral ended up being, and I'm having to look back at the screen, minus 100 times the absolute value centered at 5. Now, what this did, this created a plot which looked like so. It was minus 500 and 500. However, this beam has no applied moment on the left end, moment equals 0, and there is no moment on the right end. Now you have to remember, there is a shear on both ends, but there is no moment. So what I had is I actually had this plus a constant of integration is equal to the moment. Now, what I needed to do is I needed to make sure that my moment at x equals 0 has to be 0. And by doing that, I simply move this hat function kind of up 500. So it turns out what I did is I said, if I put in 500, that's what I have. So if you look at the moment, here's what you get. Okay, it's supposed to be halfway across, but it's 500 and it's 0. So that's the shear and the moment diagram. So here's your shear diagram, here's your moment diagram. It turns out there are other things you can do as well. Let's move across and do one more thing, and then we'll call this to a close. Now all I'm doing here is doing shear and moment diagrams. This is not necessary for the course you're in now, but I find it kind of instructive to use MATLAB to do this, to at least show you that you can do this in MATLAB. Let's do this now. Okay, now there's a principle called superposition in which you can put these together, and what I'll do is I'll do that in a second, but before I do that here, I want to basically get out here. What I'm doing is making these marks so I can, if I do this, the thing will let me have access to these areas over here to the right. So let's look at another beam. This other beam is kind of interesting. This time, I'm going to say I go halfway down the beam and stop. Now, let's say this will go to 5, and this point here will say it's going to be like 100. So if I were to look at this as a function, f of x, it would be at 0 and would have a slope of the rise over the run, or 100, or actually, since it's being pushed down, be minus 100 over 5. Oh, and times x. And so what you would have is minus 20x, but it only occurs from x to 0 to 5. It does not, the load does not occur over here. How do you do that in MATLAB? Well, it turns out there's a kind of a cool function here, and I'm going to pause here, go over and preset this up a little bit. Okay. Okay, give me a second here. And that was minus 20 times x times this is the part where I misspell things sometimes here. Here, I'll go ahead and switch screens here. Let me release this one. Okay. So now it's kind of hard to see. You can zoom this up. You probably have a high definition there. But I've got minus 20 times heavy side. Okay, now what you got to do is x. Now I may have this wrong right off first time through. But that's okay because one of the advantages is x minus 5, I think. I think that's how far it was supposed to do. Now, if I did a function plot of f from x of 0 to 10, what do I see? Well, actually, that's what I should see. It's minus sign. Did I say 20 on the other problem? Let me go see. Or was it 200? No, it was 20. So the reason it's minus and points down is because that's the load. It's pointing down. So this is actually a function. Now, what I would have done if I did not have the Heaviside functions, this is what I would have had. And it would have continued. And the triangular load would have continued throughout the span of the beam. Since I can use these Heaviside functions in MATLAB, they love those. I mean, MATLAB loves these things. And it allows you to clip off a portion. So from that portion over to the right, there is no load. So now what do we do? Let me release. Okay, so the function itself is or can be written, and I'll just say Heaviside, H for the Heaviside of x minus 5. Now, I want to go back in here. I want to do this. Integral of f dx. That's going to be my shear, which I'm going to plot down here. So I'm going to plot my shear. One of the things I don't know right now is what my left and right load is going to be. Now, what I'll do is I'll slide to the right a little bit and see if I can figure out that value in a second here. So here's what I got. Triangular load sits right here. This is equivalent to a load that's exactly 2/3 from this end, but it's 2/3 of the length of 5. So it's 10/3, and its value is 100. 100 times 5 is 500. This is a distance of 5. So it's 250. So here's what I'm going to do. I'm going to pick this right end, sum the moments about here. And unfortunately, well, you know what? Maybe I'll sum the moments on the other end. Because I know this distance and I know this distance. So I'm going to sum the moments about this end. Sum the moments about that end equals 0. This is my right load. This is my left load. Make that positive. So right times 10 minus 250 times 10/3 gives me right is equal to 250 over 3. So if this is here, 250 over 3, this is 2 times 250 over 3. So now I have a boundary condition. Again, these are considered boundary conditions. So I'm going to do this in MATLAB on the other screen, and I'm going to write it down. So here's what we're going to do. I got my f over here. I'm going to integrate f with respect to x. Oh, that's ugly looking. Okay. You know what? I'm going to go over to the screen and okay. Now, there's my function. So I did the integration, but I did not write the value v for the shear. So here's what I'm going to do. Substitute in v, we'll substitute in the value x, give me 0. Well, okay. So if I did an f plot of v from 0 to 10, I get slight problem. Okay, so on the left end, it says 0. That makes sense, but it's supposed to be 2 times 250. So what I'm going to do, so here's my shear again. V is equal to that plus 2 times 250 divided by 3. Oops. Now I'm going to do a plot of the shear. And you'll see this, okay? On the right end, okay, I get minus 83.33. What is that? 250, oops, divided by 3, 83.33. That's exactly what that is. So here is the shear diagram. That's the actual shear. Now, I'm not going to propose for a minute that I can make a good job, do a good job of that, but I'll attempt. But I'm not going to go back to the streaming quite yet when I'm doing this. So here's my shear over here. Okay. So on the right, it's minus 250 over 3. And on the right, it's 2 times 250 over 3. Good deal. So there's my shear diagram. I'll go back to the page in a minute. It's pretty ugly. So what I'm going to do now is with the moment. Now you have to remember that the moment, there was no applied moment on either end. So moment is equal to the integration of the shear with respect to x, and you get all that. So again, f plot of the moment, I'm going to evaluate it from 0 to 10 because that's where the beam goes from and to. Look at that, and what you see, lo and behold, yeah, it looks like it is 0 on the left end, 0 on the right end. There is no constant of integration. Constant of integration is 0. But notice what you see here. On the right, this looks like a linear plot. About halfway, which is about 5, it becomes parabolic looking, which actually, it's a cubic actually. If you go back and look, okay. Wow, this is pretty ugly, but you'll see an x to the third. X to the third, that's the cubic portion. There's your linear portion. So MATLAB can do a complicated beam thing. Now, I'm not going to write all this on the page back there, but here, this is pretty ugly. I'll transfer back to it, but it is very ugly what I've drawn here. Let me release. Okay, I'm back over here. All right, so yeah, granted, this looks really ugly right here. This does look ugly. This was our cubic portion right here, and this was our linear portion. So you have to think about it like this. This is first order equation. This is second or quadratic. This is cubic. This is nothing, a constant, and this being linear or first order. I guess I could say constant or zeroth order. I don't know. And so, moral of the story, which is what I wanted to get to and why I wanted to do this, is that MATLAB can do beam analysis if you're willing to look at what's called a Dirac function. And what this is x minus, say, 5. That means at x equal to 5, it has a value of 1 right there. So it's a point load. Then you have what are called Heaviside step functions, which what I did here was the Heaviside step function basically became 1 at this point and minus 1 at that point. So in other words, here is that Heaviside step function. So this one goes here, steps up to here, and goes on. This one at x equal 5 becomes, or here, let me do it this way. Here, I'll just use this space here because so let's say we look at this function. This function looks like this. Steps up at 0 to a value of 1. This function, remember, it's a minus right here. So it steps up to 1, not here, but over at 5. So this is a value of 5, and this is 1. However, I'm taking this function and subtracting this one from it. So if I take, say, f1, f2, so f1 minus f2 looks like this. Goes over, steps up at 0, goes and steps back down at 5. Then what I did is I multiplied it times a linear function, which meant that if I'm multiplying 1 times the linear function, that means in this region, I get back the linear function. In this region, the value is 0 here, I get back nothing. So with adequate use of the Heaviside step function and the Dirac delta functions, you can solve any beam you want to using MATLAB. So this has nothing to do, there's no problem like this. This is not, we've already covered all the material. This is an extra thing I just wanted to do. And I'm waiting for any questions you guys might have, and we're going to go from here.